Good morning, everyone. My name is Felippe Karp. I was a master's student at LSU under the Precision Ag Lab last year when I graduated, and this is what I've developed during my master's, which was about sugarcane yield map prediction using satellite imagery. And before we dig into this whole process, I'd like to briefly talk about the yield map because when we are in precision agriculture, we are usually talking about, I don't know if it's this in front of everything, but we're talking about a field variability. So how things change through the years and through the field from north to south or west to east. So how things change and actually how they change through the years too. And no better part of the system can tell us how those things change than the plant itself, especially for sugarcane, which is what we are actually harvesting. It's the biomass. So yield maps become an important tool for understanding this variability. So here I bring an example from a different crop. This is for corn, 3 different years, which they have yield maps for a long time, and they could build historical information. And with the historical information, they could see that the same region where you have low yields for the 3 different years are the same basically throughout the field. And also the ones with higher yields, which is in green here, it's also pretty much the same every single year. So combining all this information, we could end up with this last map, which would be a zone map, which would be used for management and managing differently the low and the high yielding zones in this field. So thinking about sugarcane, how could we use this type of yield maps? So this definitely could be used for any inputs we're going to add. So we could use the information from yield maps to generate fertilizing applications maps. But also we could use that for ripener applications. So basically where we have more biomass or we're harvesting more, maybe we're going to be applying more. And even if we can get this information about the yield throughout the field before we actually harvest it, we could actually be able to use that information for harvesting management and knowing how much we're going to harvest in each part of the field and better accuracy for how much we're going to be harvesting the whole field. So this is a few options of how we could use this information from yield maps. Well, but that's not perfect. What's the problem we have? We have a few challenges. First is the actual yield access of the for sugarcane. So for tonnage, we are talking about a very new technology that's out there, which is the yield monitor, which you have them available, but a lot don't. So that's one thing. And the second thing is actually the adoption of how much people are going to actually go there and get that information from the machine, go back to the office, process that information. And then you might say, oh, I don't need to go to the field anymore. But since I have my John Deere and it brings all the information to me already, but the thing is, it still brings the information to you with errors. So we see here, for example, error when it's starting, saying that's yielding much more than it should, and errors when it's in the end of that row and actually saying that's yielding less than it should, and also different other types of errors within the field. So this still needs to be processed. So that the question is, okay, I'm not going to do it. Is there any other way to do it? So how could we approach this and still be able to use this information or have this information more easily available for everyone, for people that have the monitor, for people that don't have it, for people that have it, it could be predicted before they actually harvesting it and being able to use it throughout the season for management purposes. So the thing is, we came up with this idea, which have been used for different crops before, which would be predict this information based on something. And this something for us is the satellite imagery, because there is a non-correlation between the imagery and the information we can get with biomass. So with that, uh, this is basically a structure of where we want to get at one point with this whole thing that we thought about. So we would start with just a very simple, which the farmer would have to provide us field boundary and season start date. And then based on that information, we would collect all the imagery for until the date that we are today, use that imagery in a machine learning system to be able to predict the yield and actually be able to provide that yield for the farmers or for consultants or for researchers, uh, even previously to the harvest. So before actually harvesting that field, being able to use that information for different type of management activities. So I will briefly go over of where we are right now with this project and what we've achieved until now and where we actually want to be one day. So first, for this project, what we have done until now, we used three different fields from 2018 to 2019 season. It was third red tune though, all the three fields, but we wanted to see if we would be able to predict even like when we would have like a very aged cane and being able to see if we still would have potential for that. We used as a real yield for those fields, a commercial yield monitor from John Deere. Um, and basically what we've done is we got those boundaries, which you can see right here in this image, there's three fields, and we got all the information from the 2018-2019 season for satellite data. So we used a satellite, which is called PlanetScope 2. It's a 3.5 meter pixel resolution, and it has a daily revisit frequency, which means it comes by to the same field every day at least. So if we have clouds and things like that, we even could be able to get good information since it comes every day. One day it's not going to have clouds, so we're going to have a good information. And it has four different bands, which is the blue, green, and red, the same thing we have in our phones, and the near infrared, which few of you might be heard about it. So this is what the sensor provides to us. And we also calculated a few vegetation indices, which is going to show us where we have more biomass or be correlated with where we have more biomass or less biomass. So we had 8 different ones. And for the image selection, instead of just getting all the images of the season, we decided we would use cumulative growth degree days and the crop phenology to be able to select a few points in the season where we would be able to have like, hey, this has a relationship with the final yield that we're gonna have. So first of all, we use the base temperature as 18 degrees Celsius for sugarcane here in Louisiana, and considered the peak of tiller would happen between 500 and 800 degrees Celsius, while the tiller stabilization would be at 1200 degrees Celsius. And with that, we decided, okay, so since we have a very long season, we want to get just for the whole season, let's establish an interval of cumulative growth degree days, which we're going to collect each image. So we decided 115 degrees Celsius, which should be around the development of 2 or 3 leaves, especially in the beginning of the development. And then we came up with a total of 14 intervals going from 115 to 1610 degrees Celsius. So we would have 14 intervals, which translates to 14 different images throughout the season. And then the next process is we have all the images. We had to bind all those images together and have one single file, and also get that information that we had in the beginning from the yield monitor and get to that image. And that's the process that's being represented in this image that I'm showing here, which we have the different cumulative growth degree days, satellite imagery, and then we combine all of them in one single image. And based on that one single image, we get the points from the harvester, basically sample those points, the fall inside one pixel, saying this pixel, this square now has this yield. And we use that as our data set for the development of the system. And for the system itself, we used a random forest regressor, which is a machine learning system. And we performed a data split, which is basically a very known thing around the machine learning, which basically use a few of your data for training and a few of your data for testing. So we decided to go for two fields for training and one field for testing. And this one field for testing is the type of information that this system, this model that we are creating is never going to see it. So it's going to be kept out during all the time while we produce the model. So we actually can compare and see how well the model can do from the data that it has never seen before. And based on this and the results, we evaluated the root mean squared error and the mean absolute percentage error in a few maps. So we could see how the prediction was being done, if it was good or not, if we could get those skewed maps or not. So showing you a little bit of where we got until now. So this is the result for the test field that we kept out. So we basically used the training data set, we built the model, and we applied the model to that test field. And with that test field, we created the interpolated yield, which is the information that we came out straight out from the machine, and we filtered, we treated correctly, and then we created the map, which is this map that you can see in your left. While this one in our right is the information that we got from the prediction. So basically from the images throughout the whole season using the 14 different growth degree days images that we have, this is the result we got. So here we are talking about an error of 3.1 tons per hectare, which translates to about 1.5, 1.6 tons per acre of error on the prediction, or it translates to 5% error overall. And when we look for the average of the field, we can see that the average for this field is almost the same for the actual yield, which came from out of the harvester, and the yield that we predicted. So this shows the potential of the system. But then we were thinking like, okay, but what about if we could predict it earlier? Can we, and when could we do that? So we created the different scenarios, total 14, which we were adding one image to every single scenario. And later on, we would just compare those scenarios based on the error and the correlation with the actual yield, and using a spot not test, which just brings us to groupings and let us know this group basically is the same thing, statistically speaking, the other group is same thing, statistically speaking. So, and here's the result that we got. So those are the correlations for the different scenarios, and those are the errors we've got. And basically, what we can see is that the best scenario we got total was from the 12th scenario, which is basically getting total 12 cumulative growth degree days with a minimum error of 3.12 tons per hectare, 1.5 tons per acre of error. While this error increases a little bit in the end, which we kind of relate to this probably with the maturity of the sugarcane ripener application or something like that. But basically, overall, we get two different groupings from the statistical analysis, in which for the first three scenarios, we would get just one single, like basically the errors are much higher when we compare it to the rest of the scenario. So basically, after the fourth cumulative growth degree day, we would be able to predict, statistically speaking, almost at the same accuracy that we would using all cumulative growth degree days. And this we can also see through the maps. So this, again, is the interpolated map, which came out of the yield monitor, and those are the maps for each scenario. And we see that even though the regions where we have low and high yields, low yields in red, orange, and high yields in green, kind of match with the regions that we also have in the interpolated map. Still, that doesn't match as good as when we move forward and we see the fourth, the fifth, and the sixth scenario here. So basically, after the fourth scenario, we basically see maps that are pretty much the same or very close to what we have on the predicted, on the actual interpolated map from the machine. So basically with this, what we are talking about is, well, according to this data and from what we have, after the fourth cumulative real degree days, we would be able to create and predict a yield map for that specifically field with a accuracy that's as good as the one we could get for the 14th. So saying that very early in the season, we could predict our yield for that field. And then we just performed a like very simple analysis here, which we used a maximum of 690 cumulative real degree days, which would allow us to do any other like application or anything still in the field using ground application. And we evaluated how we would obtain the zones of the field if we use the sixth scenario, which was max 690 cumulative degree days. And if we compare the zones of high and low yield zones from the actual harvester from the sixth scenario and the 12th scenario, which we consider as the best compared to the what we showed before, basically the sixth and the 12th are the same maps, and they're pretty similar to what we have as the interpolated. So basically, this shows that this technology has a potential for to be used for management purposes in a way that we could use the zones where we have higher yields, take a few management strategies that we wouldn't take for low yielding zones, and vice versa, and use that type of information for management, but also for harvesting purposes. So overall, what we come up with, we were able to develop a framework that allows us to get a potential for the system, and we could do in season prediction very early with accuracy that we would get from the few images we got. So there's a potential for this technology, and there's a potential of building a prediction system in which the farmer could be able, or the consultants could be able to go inside, just insert the field boundary, just insert the start date of the season, and after that, would get the predictions every 115 cumulative growth degree days. Obviously, we need to do more research, different conditions, more fields, years to be able to create a very scalable model. But still, this shows the potential. It's just a scratch on the surface of going towards this process. And obviously, here we are talking just about tonnage. We're not talking about sugarcane content, sugar content, which is something that I talk about and might be able to do. Just briefly, so let's see if I can. So if we see here, this is something that we could get at one point, which the farmer will, or the consultant could be able to have like their field in a system, which they would go and say, okay, let's see my yield and compare my yield through the prediction that we've done in June for this field, and would be able to check that every time through the season, be able to see and use this information for management purposes. Well, with this, I would like to acknowledge the farmers that provide the data and Dr. Flanagan, which helps us collecting this data, and Planet Labs, which provided the imagery for this satellite that we used for free. And that's it. Thank you. We'd like to take any questions.
I have 3 questions that have come in from the chat so far. The first one comes from James Todd. Why did you use the random forest predictor? Was it the best out of what you tested?
Well, actually, so until now, we've tested random forest and XG Boost, which is extreme boosting system. And random forest had a better accuracy, but definitely we could go above and beyond and use deep learning systems. From now, it's like, according to the literature until now for yield prediction, random forest seems to be one of the best systems to be used. So that's why we chose and we used the random forest. Also because um, random forest is a little bit simpler to explain. So there are a few things that we could actually use for management based on random forest, and a few more information that we could get out of the random forest than what we could get out of a actually deep learning system.
Everton Barreto with US Sugar asks, does your model consider skips, gaps, lack of plants in the field to calculate the yield? It would be important also on the decision to renew a stubble field.
So basically, the system uses imagery for that. So basically, we are talking about a 3.7 a meter image. So depending on the size of the skip, I would say yes. But basically, if we have a skip or we have like plants that died through because of the harvest system or whatever, if that pixel has a lower value for because there's no plant or there's less plant on that pixel, yes, that would be accounted for. And but that becomes a little bit more difficult when we go over it. So here in this, what we've done until now, used a 3.7 meter pixel and using the satellite, which is paid. When we go to free sources, we go from 3.7 to 10 meters. So this become more difficult while we go over to like coarser or free imagery to be able to account for this. But the system should. That's the whole thing, which because it's based on the imagery, which if the imagery has the potential to acquire that information, yes, we would be able to do it. Maybe using a drone image, which is much more has a very tiny pixel, we would be able to account better for that. But then there is the drawback of having to go to the field and fly it every time while the satellite just goes around without having someone to go there and fly it.
Harold Lambert asks, is the conversion of the imagery to NDVI done with commercially available software, or is that purchased from the imagery vendor?
Okay, so the whole conversion, the whole transformation, the whole process is done based on the raw imagery. So basically, if we download the imagery, use that imagery, we do code. So we use coding, we use Python to perform every single analysis for this project. So everything is done through coding. So we would just calculate in DVI and calculate everything using codes instead of using the providers calculated in DVI.
Collins asks, what parameters did you use to assess accuracy, and doesn't each model chosen have a bias toward each parameter?
So basically, the way it works here for the machine learning is the system overall uses as variables just the imagery. That's the only information I give to the model to predict. And the way that it creates the model itself is based on that and the relationship with the yield. The parameters for the model itself is defined by using a optimization process, which is very known on machine learning systems, uh, which you run different types of interactions of parts of that field or parts of your data to be able to get the most general model that you could have. So that's what we've done. One thing that it's mentioned on the literature is the thing that it needs to be like when we are dealing with spatial information for this type of activity, you need to consider that since we are using spatial information, there's a correlation because of the spatial location. So basically, where you have lower yields, all the points around this lower yield will have lower yields. That's what we consider until it goes to a higher yield zone. The thing is, based on the literature we found, we used all the processes we could for the data we have to create a model for this prediction that we presented and the results presented here that would reduce the most this autocorrelation that we could have. So this is a bias that we are not considering according to what we could do with the data we had. The other thing is what we use for the accuracy measurement is basically using the error of the model we generate. So another thing that we were worried and we took care of when we were processing this data and generating the model was to watch out for this error and how this error would be obtained for the training data set and for the test data set, which is a process that we do to not allow the model to overfit for the training data set and not be good for the test data set, which would be another bias, which we accounted for while we were developing the model. I don't know if I answered completely, but I'm open to talk more about that.